In this video, we will look at terminology that we will be using in graph theory. So first of all, a graph consists of sets of dots called vertices. Each one is a vertex, and a set of edges that connects those. So let's take a little more formal look at the definition and an example of those two words. So first of all, a vertex. A vertex is just a dot in the graph where the edges meet. An example here is G would be considered a vertex, or C would be considered a vertex. The word vertices is just when we're talking about the plural, right? So E and A are vertices of this graph, all right? Something to notice is that vertices only occur when a dot is explicitly placed, all right? So if there is no dot and it looks like edges are meeting, don't assume that they do. An example I'll show you more about later would be to imagine a freeway overpass where the freeway and the side street cross, but it is not possible to go from one to the other. We'll look at an example about that in a second. The second word is edges. So an edge is basically a line segment in the graph that connects vertices. All right, so there's an edge that connects G and C. There's another edge that connects G and H. All right, let's go back and look at that example I'm talking about. Now here is a couple snapshots from Google Maps of a location in Fresno where Highway 41 meets Highway 180. And this is kind of a look at just the regular 2D map. And so you can see that there's a lot of connections that are on this map. For example, on the side streets, if I look at the side streets, there's this street here, Belmont Avenue, right? And it intersects with some other roads, right? There's another road here. Well, those roads truly, you can go from one to the other. So it makes sense to put a dot there, a vertex, right? So if we go up, we could put a vertex here because we can connect in different directions. You can often turn, on a street. Whereas on the freeway, it's not necessarily true that 180 and 41 should have a vertex. Now let's take a look at why. So over here, I changed the Google map to be more of a three-dimensional view. You can kind of get a sense of how those maps, of how the roads overlap each other. And then here's a close-up view, right? So certainly if you're a car traveling here on Highway 41, and that's not going to be the most beautiful car. That's my best picture of a car, right? You're headed this way. You're actually just going to go underneath this bridge and come out the other side and keep going, right? There is no need to put a vertex, even though, like, if you look straight down, it looks like they cross. So what's mean by this is if you have an edge and you have another edge, but there's no vertex explicitly shown in the graph, like there's no dot there, then there's no intersection, right? You assume that you can't make a change there from one to the other. And that would certainly hold true in the picture, right? If you're a car up on the bridge here, you certainly don't want to even try and get off on this road here. That would be an accident, right? So that's what we mean by placing a vertex only being explicit. A special feature of a graph is called a loop. A loop is a special type of an edge that connects a vertex to itself. So in this picture we have here, I have this vertex. I'll call it just vertex A right here. Okay, and maybe this one is B and this one is C. Certainly A connects to B along that edge and A connects to C along that edge, but A actually connects to itself on this loop. And those exist in the real world, right? We often have roads, maybe a road intersects another road, and then that intersects another road, but maybe within that, there might be a place where you can kind of go in and kind of do a loop and come back. All right, that can totally happen. All right, let's take a look at a formal definition of what we're going to call a path. A path is a sequence of vertices. Notice that sequence of vertices, and we'll write a path down by just listing the vertices in order with the property that each vertex in the sequence is adjacent to the next one. Okay, how do you get from here to here to here in order? So thus, a path can also be thought of as describing a sequence of adjacent edges and edges that are next to each other. A good way to think about a path is a trip, right? When you take a trip, what are you doing on the map? The key requirement in a path is that an edge can be part of a path only once. Okay, you only travel down an edge once on a trip. You don't go down the same edge twice on a trip from here to there. Now, of course, there might be a return trip, but we're just talking about a one-way trip, path. All right, that's kind of a way to think about it. If you travel along an edge once, you can't travel through it again. All right. On the other hand, this is key. On the other hand, a vertex can appear on the path more than once. Kind of interesting. So you can come to the same intersection. You just can't go down the same road. So let's illustrate that here with a few different graphs that I have here. So here's the graph that I showed from above. So a trip or a path would be a way to get from one place to another. Let's look at a path from A to G. All right. So first of all, there's lots of answers. And then how would we write that down? Well, you might think like, well, there's a really easy way to get from A to G. I go up to E, and then I could go over to G like that. That would be the path starting at A. We would list A first, and then E, and then G. That's what we mean by adjacent, right? The actual path drawn out. But there's other ways to get there. For example, you could go from A to B, and then you could go from B to F, and you could go from F to H, and H down to D, and then D over to C, and then C up to G. That would be a scenic tour, right? A scenic trip. But it also would be a path, A, B, F, H, D, C, G, right? So a lot more roads to get to the same result, right? Lots of edges that we traveled on there. Here's a couple other examples of possible graphs. Notice that each one of these contains a loop. So I might ask for like, oh, what is a way to get from, let's see, A to B? I'm going to go from A to B. Well, the easiest way is to say, well, just start at A and go directly over to B. That would be just the path A, B. All right. But are there other ways to get from A to B? Yeah, of course. You could go A down to C and then up to B. That would be A, C, B. And would there even be a way to use the loop? Absolutely, we can use the loop to get from A to B. We could go A, first go down to D, then over to E, and then we could loop around the E. Now notice we came back to the same vertex, but that's okay in a path as long as we don't repeat the edge. And then lastly, travel around this edge to B. So this one's a little more complex to write down, but it would look like this: A to D to E. Now, since you were at E, you went around the loop, you landed at E again, you write E twice, right? A, D, E, E, and then back, I mean, not back, but over to B. So that would be a path. Now, notice that this one would have sort of length 2. We call the length the number of edges that you, I wrote that incorrectly. Length 1, pardon me, the number of edges that you use, right? So we just use one edge there from A to B. But the next one uses 2 edges, right? A, C, B. And the last one would be 1, 2, 3, 4 edges to get from there to there. All right, I'm going to pause my part of the video and I'm going to ask you some questions about this graph to the right-hand side and have you think about it. Okay, now that you've answered those questions, let's talk briefly about a couple more things. One is a connected graph versus a disconnected graph. A graph is connected if there's a path from any vertex to another, right? And it's disconnected if there's not. Now, in this example, if this was A over here on this bottom right vertex, and this is B at the top left, there's no way to get from A to B because the graph is disconnected, all right? Connected graphs, there'll always be a route no matter how obscure it is. Now, you can make this a connected graph just by connecting one of these. If you connected one of those to each other so that you could get from A to B, then it would become a connected graph. So that's a word that will come up. Lastly, last thing I want to touch on is that graphs can look very different. If you look at these three, well, they look vastly different. But when you examine them closely, these are actually the same map or the same graph, which is it's hard to believe at first. But let me show you a couple of reasons why, and then you can play with it and discover it yourself. Look, for example, if I wanted to go from A to D through L. All right. So I'm going to start at A, and I want to go to D, but I want to go pass through L. So one way to do it is go directly to L, right, and then go up to D, just like that. Now, if you look at the map in the middle, you would start at A. You can go directly to L. Now, there's a direct route, right? There's one edge right here. It's pretty curvy, but there it is. And then you can go from L directly to D along this curvy path here, right? And the same thing for the one on the very right. If you start at A, you can go directly to L and then up to D. Now, the thing that's easy to notice at first, that you can do all those with 2 edges. The thing that's not as easy to notice is the number of connecting paths to each one. Like if you look at A, for example, notice it has 1, 2, 3, 4, 5 edges connected to it. And the next map, 1, 2, 3, 4, 5. And the next map, 1, 2, 3, 4, 5. And so it turns out that what's really important about graph theory is how you connect the vertices to the edges. And as long as the Connections are all the same. There's the same number of vertices and same number of edges and the same connections in the same way. It really doesn't matter the way that you draw the map. So that means when you're drawing a map, which one's better? Is it the one on the left, the one in the middle, or the one on the right? And the answer is it depends. Do you want it to look more like the reality of what you're trying to map out? Or do you want to draw it in a way so that it makes more sense and so you can find connections? And these all become important questions as we examine graph theory. All right. Hope you enjoyed this introductory video, letting us know a little bit more about the terminology.